Well, thank you all for being here, and I'm very grateful for the opportunity to visit Japan again and participate in this wonderful conference where I hear the word chirality at a higher density than I've ever experienced. So that's good, and it's wonderful to talk. And of course, there'll leave time for the questions at the end, but if people want to interrupt along the way, I would welcome your interruptions. And I want to tell you about, by way of introduction, that I'm going to talk about some unusual ground states and active dynamics of liquid crystals in various contexts. I'll start with a sphere. That's a fairly old story, something that was worked on by Vincenzo Vitelli back when he was doing his thesis. And many of you know, of course, that you can't comb the hair of a sphere without singularities. And here's a polar order parameter with the North Pole. You can't see the South Pole, but if you take an energy minimization approach, there's a energy which goes logarithmically with the radius of the sphere, and there are two defects, as I said, one at the North Pole and one at the South Pole. It gets more interesting if I make these double-headed arrows, because if they're double-headed arrows or just rods, as would be the case for nematogens, then this might be a little zoom of the northern hemisphere. This is a plus one defect that's still sitting there, but that's unstable because the lowest energy defect in this case is a plus 1/2, and you'll get two plus 1/2s that will then push each other apart because it's very much like electrostatics. Similar thing happens on the southern hemisphere. This is a nice picture because I know in Japan, baseball, this is actually a softball, is very popular. In fact, these defects are repelling each other, and in this very simple context, they go and sit at the vertices of a tetrahedron. That's the way they can get furthest apart. And then there's a background Gaussian curvature. It's a little bit like a Jellium model of a metal, perhaps, with four charges, four, in this case, topological charges, with a background Gaussian curvature. And there are experts in the audience on other things that you can do with this problem. I wanted to just mention that there's a theorem that goes with this that many of you probably understand better than I do. It's a Poincare-Hopf theorem, talks about the net defect charge with certain topologies, and in this case it must be 2, which is equal to, of course, 1/2 plus 1/2 plus 1/2 plus. Okay, so people in the audience have done beautiful things like Zvonimir and Mark Bowick and their collaborators, where you actually realize this tetrahedral thing, but you realize it with active matter. And if I remember correctly, this is a vesicle with microtubules and motor proteins near the surface, some cortical arrangement of them. And these defects are certainly there, all four of them, and they're whizzing around like some sort of strange planetary clock. And so that's going to be something that I'll try to embellish on a little bit later in the talk, but in a somewhat different geometry. So with that introduction, I want to actually tell you about defect absorption and emission for liquid crystals on cones. And I'll try to tell you why cones are interesting. I often used to think that they were kind of boring. They have essentially zero Gaussian curvature locally, but as you'll see, there's an important delta function of Gaussian curvature that's going to play a role in determining the ground states of liquid crystals, for example. So we'll start by talking about a very simple problem, not a cone, but orientation order on disks, the role of boundary conditions, and so forth. And then we'll get to understanding these kinds of textures. We're going to look at how to comb the hair of a cone. And we'll also be talking about dynamics, which I'll get to in a minute, or maybe more than a minute. And I'd like to convince you that a cone, for all the simplicity of the geometry locally, is really the soft matter analog of the Aharonov-Bohm experiment. A very important application of quantum mechanics. Here is the phase of an electron. Here's a solenoid. And depending on whether the electron goes around one way or the other way, there's interference downstream it detects the presence of the vector potential even though the curl outside the solenoid is 0. And that's a similar thing that goes on with this cone. The Gaussian curvature is basically 0 on the flanks of the cone locally, but there's a delta function of Gaussian curvature which can be detected by liquid crystal molecules arbitrarily far down on the flanks, similar to the way the electron detects the flux through the solenoid. And the analog of the flux will be determined by the cone angle here. So that's what we'll be talking about, and ultimately we'll put in some dynamics, and you'll see that the tip of this cone can, unlike the Aharonov-Bohm experiment, emit and absorb defects. So these are the people who did the work, Farzad Baffa, who's a postdoc, and Grace Sean, who's my graduate student. So let me say why this might be interesting. That's probably not necessary too much for this talk. Cones, although locally flat, are a kind of Green's function problem, an problem for geometrical frustration, because all the frustration is concentrated at a point. And you'll see that the defects on any curved surface, including cones, interact not only with themselves, but also with whatever Gaussian curvature is present. On a sphere, that Gaussian curvature is uniform, but here it's going to be concentrated. And if you know the distribution of Gaussian curvature as a function of coordinates, as shown by Vitelli and Turner, there's a kind of Green's function problem where there's a potential, a geometrical potential that will play an important role in what I have to say. But here's a biological example of cones. You could look at crystallography on cones if you like. I'll be looking at liquid crystal order, but you can look at hexadics on cones or tetradics on cones, and there's all sorts of interesting things that go along with that. Here's a picture of a protrusion from a confined cellular layer, and this protrusion is a model. The protrusion is coming up, making clearly some kind of conical geometry, and there can be a order parameter with p equals 1 or p equals 2 symmetry, a vector or a nematic symmetry. In that case, and of course, you can have other types of Gaussian curvature. This is a beautiful picture, I think from the Technion, a group at the Technion, which has arms coming out, and there's clearly perhaps conical singularity at the end of this appendage as this thing develops limbs, but there's negative Gaussian curvature in the armpit, for example. So that's kind of motivation. And I now want to back off a little bit and talk about a somewhat simpler problem, which is what happens on disks and the important role of boundary conditions. So this is a famous model of liquid crystals just for calculational convenience. I put it on a lattice, but imagine it's really a liquid crystal. Here are the orientation angles. P could be 1, 2, or could be 4 or 6 if you want to look at more exotic kinds of order. And there's a Gaussian field theory that comes when you expand this cosine and some kind of coupling constant that tries to align the director field, as many of you know. Now I'm going to impose tangential boundary conditions on a disk. The disk will be deformed into a cone at some point. But if this disk with radius r, if I just have polar order, I go around the edge of the disk with tangential boundary conditions. And in both these cases, actually, the winding number as I go around has to be a total of 2 pi. And so there's a single defect which sort of just sits boringly at the origin for p equals 1. That's sort of like a polar order on the northern hemisphere, but this happens to be a disk. With the same tangential boundary conditions in p equals 2, this splits, just like I showed for that baseball, splits into 2. And those 2 go out toward the edge, but with the tangential boundary conditions, there are image charges. In a kind of electrostatic analogy, like sign image charges that keep these from going all the way to the boundary, and they stop, and you can show for a p-fold symmetric order parameter, they go out a certain distance, which is given by this formula here, which is derived by Farzad and Baffa. And we've checked that numerically. Now, ultimately, I want to ask, let us promote these nematogens in the beautiful way pioneered by Aharonov-Bohm and others into an active nematic. Then locally, these look like little comets. They start moving, and we want to see ultimately both for ground states and dynamics, how does the cone geometry differ from a boring flat disk that I just showed you? Not entirely boring. Well, this gives you an indication of some of these are trajectories of defects on a cone that I'll get to later. We think it's a kind of intriguing problem, and welcome your feedback as I go through this presentation. So this is a little bit of differential geometry of the cone. We distort the disk into a cone, and now it has this point up here. And this is a parameterization of the cone. Sometimes it's convenient to parameterize by flank length. The cone has a geometrical frozen parameter beta in these calculations. That's this cone angle that's continuously variable, and then there's an angle theta that takes you around. So it's kind of strange conical version of polar coordinates. And you can work out all the things that are beloved by differential geometers like the metric and so forth. So here's the metric. And importantly for us, an elementary application of the Gauss-Bonnet theorem tells you that if I have a circuit, any circuit that encloses this apex, like this circuit here, or this circuit down here, it doesn't have to be a circle, it could be some strange loop that goes around. The integrated Gaussian curvature, here it is, it's a function of these polar coordinates, associated with everything from these boundaries, the base, it looks like a local base of a cone, all the way to the top. That integral is frozen. It has to be 2 pi times 1 minus sine beta. And I'll often denote 1 minus sine beta chi. It's a deficit angle, as you'll see as we go along. That's it reflects a kind of delta function of Gaussian curvature. Everywhere else it's 0, but there's something going on at the apex. And even if you snip off the top of the cone, it's still there. You can detect arbitrarily far down on the flanks what's going on. And of course, the reason for this, the consequence, if you like, of this, is that if you just try to parallel transport this order parameter and make it as parallel as possible to its neighbor, there are Christoffel symbols, which play the role of a vector potential here. And this thing rotates as you go around. And so in this particular cone angle, it rotates by 180 degrees. And locally, everybody's happy. There's tangent as parallel as possible. But here there's a real problem coming back, at least if it's a polar order parameter. If it's nematic for this particular cone angle, it's okay, but for general cone angles, there's going to be geometrical frustration. This is perhaps the most primitive, but I think rather striking example of geometrical frustration. So chi has the interpretation of the fractional area that's removed. So you can, cut out a sector of a disk and then tape it back together. I actually did that just before the talk, and I'll talk about these and pass these around in a minute. But of course, you don't have to take out area, you can add area. And what I have here is a hyperbolic cone. It looks a bit like a saddle. And we can ask what are the ground states, the liquid crystal textures on these hyperbolic cones, which I'll be coming to also in my talk. Any questions at this point? Have I made myself understandable? Someone's nodding, so I'm going to go on. All right, so what happens to this Meyer-Selpa energy on a cone? It acquires something that looks an awful lot like a vector potential. We can write out what it is, and we can work it out. There are various commensurate cone angles that are easy to do calculations, but for arbitrary chi, it's known. And it's a problem that looks a little bit like a superconductor, perhaps in the London theory of superconductivity. It's also, as you'll see in more detail, a conical Aharonov-Bohm effect. Here we have various values of chi. These are values of chi that allow you to tile the cone with a perfect triangular lattice. There are other values that allow you to tile it with square lattices. And we've done most of our calculations at these special values, but the theory, it seems to work for general chi, or we expect it to work. So here are these various chi's, and you can see, again, there's geometrical frustration if I just blindly try to minimize this square. You think it's an integral over a square, so you make this thing 0, and that's going to minimize the energy, but then there's this problem coming around. There's a discontinuity, which would cause an enormous amount of energy. So the system has to find some kind of compromise, a different compromise for each value of chi. As I look at this, and in fact, it's basically a problem of layered or stacked Möbius strips. And you have to fit these strips together in some fashion, and the defects may or may not be helpful in doing this. They certainly play an important role, at least indirectly, and sometimes very directly in determining the ground state. So it's a Möbius strip-like problem, and moreover, we had those nice tangential boundary conditions that, for a disk at least, but tangential boundary conditions are incompatible with parallel transport. So this is just an illustration for a cone with tangential boundary conditions. But if I let the vector potential of parallel transport act, you rapidly go away from that. And so something with tangential boundary conditions is itself geometrically unhappy at the cone base. So here is a ground state of a cone. Here is two such cones that reflect what you just see there in that picture. And you can ask you can do the following Gedanken experiment, which I will set up with a baseball, which I'm also happy to pass around, although I would like to get this back. So here's a baseball. This is the baseball with these 4 defects sitting at the base, at the points of a tetrahedron. And I've drawn an equator. I'll pass this around, as I said, a red equator. That red equator has the tangential boundary condition just done perfectly. So imagine I take the northern hemisphere with its smooth Gaussian curvature, and I deform it into a conical point. Let's ask what will happen. There are 2 defects in the northern hemisphere, 2 defects in the southern hemisphere, and they will presumably move around and adjust in some way. So let me start passing that around. And well, of course, you can look on the surface of this cone, and here's one of them sitting on the flank. So this is this was what happened in the northern hemisphere and this Gedanken experiment. But if I rotate the cone around, the other defect has disappeared. Where did it go? It was eaten by the apex. The apex eats defects, but not all of them. So that's one of the things that we found interesting about this problem. Here's the baseball. Let me pass the cones around. I'm sure you all want to play with cones. Cones over here. Cones on the right, cones on the left. And so when we got these results, I kept looking on the back side, and where's that other defect? And it's not there, as you can check. You can't see it in this picture, but it's definitely not there. And so, in contrast to a hemisphere, one of the defects has been disappeared and basically hiding, as you might have guessed, at this apex. So you could actually look as a function of chi, and here's the disk that I talked about at the beginning with its tangential boundary conditions. It turns out for any non-zero chi, all the way up to 1/3, one of these defects gets eaten. So this is the top view of the cone. Here's the surviving flank defect, which is one at the apex. And then if you go up to chi equals 2/3, or actually anything greater than 1/3, the second defect gets eaten. And if you put a hexatic on a cone, there are 6 defects on the flanks. And there is a serial devouring of each one of the 6, one after the other of these 6 defects, as the cone gets pointier and pointier. And there's kind of phase transitions in the ground state where these defects get eaten. So this is the Poincare-Hawk theorem illustration, and I would urge you to take it with a grain of salt. Of course, their theorem is has, I'm sure, caveats about smooth surfaces. These are not smooth surfaces, but it's not always right. You have to be a little careful, especially when there are these singularities. Okay, how do you get analytic results? I don't want to spend a lot of time on this, but there's some beautiful work by Farzan Fafa, who has many talents. One of them is he's a person who knows his way around the complex plane. And so he knew, as other people, I'm sure Mark Loeb knows this kind of stuff, conformal mapping, isothermal coordinates, and it is a beautiful transformation that takes a cone with an angle beta and basically squashes it down so that it looks like a disk at the expense of having a singular metric. And so, again, I'm not going to go into the details, but the metric has this nice form where it looks locally flat, as it should be. It's a cone after all, but there's this stretching conformal factor here that stretches, and that's just actually chi, this deficit angle, times the logarithm of z times its complex conjugate. And so it's going to look like a disk in these new conformal coordinates, but that disk looks like it has a charge, actually. At its tip, the charge at the tip is actually going to be minus chi, it turns out. So if you think in terms of electrostatics, it's like there's a charge there. And for each charge inside the rim, if you want to enforce the tangential boundary conditions, there's this, that's a charge inside. And then in this nice coordinate system, there's an image charge, like sign image charge. If they're free boundary conditions, it's opposite sign image charge. You can get nice results for free boundary conditions. Okay, with that discussion, I'm going to turn to dynamics, but before I go on, are there any questions at this point? I'm happy to answer. Mark.
So what happens with that defect absorption? What happens with that defect absorption when you chop off the apex?
I'll show you an example of a ground state. It's a great question. You might think that a lot of this is associated with having a very sharp singularity, but if you chop it off and it's a small hole compared to the dimensions of the cone, it doesn't matter. Very much like taking an Aharonov-Bohm experiment and expanding the radius of the solenoid. So it's very insensitive to that, and this Gauss-Bonnet theorem still works. What effectively you do, Mark, when you chop it off, is you put free boundary conditions on the edge of that wound that you create, and then it can absorb and emit defects as it wishes, which is essentially what's happening, even if it's arbitrarily pointy. Thank you for the question. Yes, please.
I have a question on the experiment. Like, how does the experiment look like? Like, would you make physically a cone of some solid material and put the liquid on the surface of it?
Okay, so we have many experimental experts. Here is an experiment which, in my view, urgently needs to be done. Yes, the short answer is yes. Imagine using 3D printing to make something with a cone. It could be a decapitated cone, as Mark always mentioned. Put a liquid crystal on with some activity, a one-on-one activity in the end. And in particular, I'd love to see people do these experiments like with Quincke rollers and a banked track, like European bicycle races, because that's nothing more than a decapitated cone. And bicyclists going around the banked track and Quincke rollers or some other analogous thing where there's a broken symmetry and things go into active motion. I'll show you an illustration in a minute. I think all sorts of intriguing things should happen. So love to see some of these classic experiments where you have a racetrack and self-organized moving things, toner tube type problems, and as you said, liquid crystals on a cone with tangential boundary conditions lying in the plane of the cone in that sense, but maybe tangential boundary conditions at the base. So thank you. Other questions? Yeah, please.
If you put a kind of spherical, actually spherical cap on top, that sounds more biologically possible.
Oh, of course, we want to heal, and close off things with a nice spherical cap. The results won't change. If the surface area of that sphere is small compared to the total area of the flank, far from that sphere, spherical end cap, you won't know. There's a question in the back.
Can you also solve it numerically on a plane and then just use problem mapping?
Yeah, so that's basically what we do, but we solve it in the plane with a defect charge that depends on the cone angle. So there has to be a central, that's kind of, I won't call it a central charge because that's already been taken by the string theorists. But there's a defect charge at the center. If you can solve that electrostatic problem with the right boundary conditions, and you do it carefully, there's some subtleties there, you can figure out what's going to happen. But I now want to talk about what happens when we have dynamics. What happens when the defects move? Okay, so we have the time here. All right, good. So this is a model of dynamics, and we're going to add activity. And for those who aren't experts in active matter, and I'm still learning this subject myself, you describe a nematic by a two-dimensional traceless symmetric tensor Q. It's a 2x2 matrix field, and there's some hydrodynamic equations that describe how this tensor changes in time. There's sort of very simple advection, the U dot grad Q would occur in almost any hydrodynamic problem. But there's also rotational and shear terms that come in here. You'll see what they look like in a minute. And then there's a kind of a local molecular field that causes this thing to relax back to equilibrium. So that's one of the two equations. That's for the order parameter. I'll show you the numerical solutions in a minute. This work with Amin Dost-Mohammadi and Farzan. And then there's just some simple, imagine a liquid crystal film, fairly thin on it with no slip boundary conditions on a substrate. And then there's some frictional coefficient for this U. I need a U equation for U to complete this thing. There's a viscosity, there's a pressure tensor. And the important thing for us is there's going to be gradients not only of the elastic stresses, which are of course always occurring in these liquid crystal problems, locally planar. There's also going to be activity, and that's one of the wonderful discoveries in this field of active matter. And if you want to do a dynamical version of this using these beautiful and powerful conformal coordinates, Farzan worked that out, and he has his own personal notation, which it makes a lot of sense, but it takes a while to get used to. But it's basically the same equations, but now set up in such a way that we can take advantage of these simple conformal factors on the cone. And this is the result of the local molecular field, this term and this term. That's what this df and q star is. V is just a complex velocity in the complex plane. So I won't go into the details, and alpha could be extensile or contractile, as experts in the audience know very well. And in the overdamped limit, which is mostly what I'll concentrate on simulations, then there's a velocity which goes like alpha times the gradient of q. So the question is, what happens when we do this on a cone? It's well studied and beautiful things done in planar racetracks on spheres, as many in the audience know. And we're going to simulate simple compressible fluid flows, some overdamped limit. We have not going to put in thermal noise. There's an interesting question. What is the Copulus Fallis transition on a cone at equilibrium? I don't think we know for sure by speculations, but something that I'm trying to understand better. So here's some simulations. The simulations in this case, we're seeing actually a disk. So we'll start with the disk. Those are relatively easy to understand. And it was convenient for Farzan and Amin to put 45-degree, not tangential boundary conditions, just to make the dynamics a little more vivid, but it's still more or less the same as tangential. And here we have the two defects that were sitting in that boring disk-like ground state. And if we now add activity, you can see that they orbit around at a deferred radius, and you know, like perpetual motion machine, but it's much like that topological clock for spherical active matter. And you can show that they orbit in at least with some reasonable approximations that at that dynamics you can show that they orbit with a there's a polarization vector associated with these defects, right? They're like little comets. They have something tells them which direction to go in locally, and there's this angle phi that is constant on this kind of motion, for this kind of motion with these 45-degree tangential boundary conditions. So now I'm going to repeat the simulation, or what was repeated by my collaborators. And now there's an X in the middle, and that's just to remind you that there's an effective topological charge. I guess maybe you should call it geometrical charges. These are the topological charges, the usual ones, +1/2. But now, if I have a cone with a certain cone angle, in this case, pi is 3/5. There's effectively a charge -3/5 at the origin that's going to interact with these guys. And it has opposite signs. So the question is, what's going to happen? So I'll run this movie as well. And you can see that one of the two +1/2 defects is immediately eaten by the -3/2 defect at the origin. It's trying to become charge neutral, but out of equilibrium in a dynamical way. But it can never become arbitrarily neutral because the topological defects are quantized to be integer multiples of 1/2, but the cone angle is continuous and generically incommensurate with being completely canceled. So we have a net charge in the system, and this is a kind of 3-body problem. We started with 2 defects outside and then one at the center that's frozen, and so it's a 3-body problem. I'll come to a 4-body problem in a minute. And we use something which we call the Born-Oppenheimer approximation. How many of you have seen the movie about Oppenheimer last? Okay, everybody, I saw it. And you know, in fact, there's one point in the movie where somebody comes up to the young 21-year-old Robert Oppenheimer and says, "Oppenheimer, I love your theory of molecules." Well, they're talking about the Born-Oppenheimer approximation, where electrons move very, very quickly to rearrange themselves to accommodate what the nuclei are doing in like a hydrogen H2 molecule. And we're doing the same thing here. We're basically assuming that the defect determines the texture. And that's this problem is sort of a borderline case. It barely does, but it seems to work. It didn't have to work as well as it did, but it seems to work, where the texture instantaneously responds to what the defects are doing. So we can now go to even larger activity, still with chi equals 3/5. So we can certainly do that and ask what happens in that case. And then something more interesting happens. I thought the other thing was interesting, but this is also, I think, worthy of attention. I don't know if you saw, I went by pretty quickly. Let's wait a little bit longer. I might stop at another point here. Keep going. So I don't know if you saw it, but this apex is periodically emitting and absorbing an anti-defect. And in fact, if you look at this thing long enough, you'll see this little thing come out, this little blue triangle. That's a -1/2 defect, which is emitted by the cone, and it's like a killer drone. It tracks down one of the +1/2 defects and annihilates with it. And with this, in this high activity regime, it's actually a very chaotic problem. It's emitting and absorbing defects seemingly and destroying defects at random intervals. And, it doesn't have to be a 4-body problem. It could be more complicated. If it's hexatic order, then there's probably some chaotic dynamical system that is underlying all of this. So if I summarize these active nematics on cones, I can say, well, here's a little picture of what's going on. This is a kind of there's a capture radius. This is maybe the apex of the cone. This is a blow up of the dynamics of these +1/2 defects. This is one that's about to go in and be captured, as was shown maybe 2 movies ago. And so sometimes it makes it, sometimes it just goes off to infinity. And there's a little sort of capture radius that Barzan was able to work out exactly. The polarization is this local direction. I talked about how that's conserved in simple context. And the actual radius when these things are rotating is determined by a compromise between the Coulomb repulsion between 2 +1/2 defects, the attraction to the apex, and the activity itself. So the activity gives rise to forces that are radial and tangential, and the radial component of the active force helps set the radius. The radius changes when you turn on activity. There are these transitions via apex-mediated defect absorption, pair nucleation and emission, killer drones, stuff like that. Here's our tentative phase diagram, burning up a lot of computer power at the Niels Bohr Institute. So there are 2 axes of interest here. One is the deficit angle, which is not actually chi, it's 2 pi times chi. That's the fraction, chi is the fraction of the disk that you're removing. And then, some analytical stuff. I think this blue line we know analytically, but otherwise it's just a kind of in silico exploration. We need experiments to find out what really happens. But at high activity, lots of intriguing things happen, not merely defect absorption and emission, but some kind of chaotic emission absorption thing where 2 goes to 1 on the flank, goes to 2, goes to 1 at irregular time intervals. In space-time, these defects will be braiding. Okay, they'll be braiding as they move in time. And so we'd like to know what that braiding entropy is as we go out to a large activity. And out here is terra incognito. This wiggly line is probably not horizontal. But way up here at high activity, we have some chaos, indications of chaos, which we're trying to characterize. I want to conclude. I want to leave 5 minutes for questions. So I just want to quickly just talk about, and we had questions along the way, but I'll try to finish with time for more. The differential geometry of hyperbolic cones, where again we can use the Gauss-Bonnet theorem that talks about these 2 curvatures. This is integrated around the surface. This is the Gaussian curvature integrated over an area. The Euler characteristic is 1. Don't worry about that. And make a long story short, for a simple model of a hyperbolic cone, I won't tell you about the model. Here it is. We can look at what happens to the normals, and Gauss tells us that you can detect that Gaussian curvature again by going around the loop. And we've actually worked out what that integral is in terms of the geometry of this hyperbolic surface. And here's what the nematic ground states look like. I didn't have enough energy to make one of these models pass around, but it's a hyperbolic cone, and you'll have to take my word for it. And we did the numerical calculation. This is just the ground state. We haven't done the dynamics at this point. There's 2 defects on a disk. We make it a little bit hyperbolic, and all that happens is 2 defects stay on the flank, you might have thought. But instead of, this is chi equals minus 1/3. So I've added 1/3 of a disk for minus 1/2. You get 3. It belches out a new +1/2 defect. And there's a phase transition as a function of chi, and you go to even larger negative values of chi, you get 4. So I want to wrap up, so there's time for some questions. I've talked about combing the hair of a cone. Here's with three boundary conditions. And you might imagine that there's a chiral broken symmetry, some of these ground states, right? You can comb it with this swirl or the other swirl. This is with the tangential boundary conditions that I talked about before. I've talked a little bit about hyperbolic cones. This is a convenient, it's only approximate, we think, but convenient parameterization of the shape of a hyperbolic cone. And this parameter A plays the role of the cone angle beta for a hyperbolic cone. By the way, even geodesics are non-trivial on cones, right? A cylinder, if I have a cylinder and I have 2 points, I want to ask, what are the straight line trajectories? There's an infinite number of them typically, because you can spiral around and it's all going to be a straight line when you unroll the cone. Here, for this cone angle, there are 3 geodesics connecting this point to this point. There's the shortest one, but there are 3. And then different cone angle, there could be 4. This is Mark Boek's question. Decapitate, calculate ground state. There it is. Same flanking effect as before. The last slide is about cone geodesics. I don't know, there may be people know more than I, but we just had a lot of fun with these cone geodesics, because if you take these cone geodesics and look at so you know, certain cases the defects will follow geodesics, so worth knowing what they are. Geodesics on a cone can act like a boomerang. You try to shoot a geodesic off a cone, it goes up, and unless you aim perfectly for the top, it starts to change its mind and come back at you. So there's another dynamical systems problem that we're trying to explore. So thank you very much for your questions and your patience, and I'm happy if there's time to answer any more questions.